Hello everyone. This is the video for Monday that you'll need to watch. And we're just going to conclude section 3.2. So a lot of this that I'm going to go over sort of the last few pages in that section. You already know about equivalence relation and equivalence classes. So this is just something a little extra. So it's nothing really new, but it's something to add in terms of when we talk about equivalence relations and classes. So you may want to stop, pause this video to copy this definition, that example down, and then we're going to move on. So here we have a definition. Let m be a fixed positive integer. For x and y in the integers, x is congruent to y modulo m. If and only if m divides x minus y. So we write it as x congruent m y, or it's usually denoted as x equals y mod m. Okay, so we usually use that notation. And the number m is called the modulus of the congruence. So for example here, I have 3 equals 6 mod 3, since 3 divides 3 minus 6. And 3 minus 6 we know is negative 3. And also, and then we can also say that 4 equals 1 mod 3, since I'm going to go back, since 3 divides 4 minus 1. Okay, so that's the definition of x equals y mod m. Okay, so now notice or note that 0 is congruent to 0, 3, negative 3, 6, negative 6, so on, etc. in mod 3. Right? So if you think about that, because 3 divides 0, take it. 0 is congruent to any of those two because you can take any of those two numbers and it'll divide. 3 will divide those. Okay. So in fact, 0 is congruent to every multiple of 3 in mod 3. Okay. 0 is congruent. All right. And so we have... So let me clarify. I don't want to make sure I don't confuse you all. So what this statement is saying here, so 0, 3, any multiple of 3 in mod 3. So 0 is equal to 6 mod 3, since 3 divides 0 minus 6. Okay, and we can continue that. So that's why 0 is congruent to every multiple mod 3. Okay, so we have a theorem that we're actually going to prove. And that theorem says for every fixed positive integer m, okay, the congruence m, so the mod we just defined, that is an equivalence relation on the integers, on Z. Okay, so again, remember what that means. So in other words, what we'll be showing, or what we need to show, so this isn't part of our proof yet because I didn't put proof, but what we need to show is that x equals y mod m is an equivalence relation on Z. Okay. And you all know again what that means to be an equivalence relation. To show something is an equivalence relation on some set, in this case our set is Z, we need to show that that relation is reflexive, symmetric, and transitive. Okay, so we're going to prove that. Okay, so now let's start our proof. And we're going to let M be a positive fixed integer. Okay. And what I actually want you to do is right here, well, let me do this first. So we need to show, so first in our reflexive property, we need to show that x relates x. Well, in this case, that means we need to show that x equals x mod m. Okay, and what I would like you to do is pause the video here and see if you can actually prove this. So see if you can do the proof and then play the video again, because I'm going to actually pause the video and write down the entire proof instead of just going over it to save time on the video. Okay. Okay, so hopefully you tried that and you have something along these lines. So again, we need to show that x equals x mod m. Well, first, let x be an integer. Okay, so that's what we say first. Okay, in your show part, I simplified, I didn't extend it out, but hopefully you extended it out or thought about what that meant. So x equals x mod m means m divides x minus x. So if you can show that m divides x minus x, then you've shown that x equals x mod m. All right, well, now you have to think about, and this is what I said, sometimes reflexive can be the hardest thing to prove because you sort of have to think about how you can say something without actually just saying it straightforward. Well, here's what we have. M times 0, we know we need to bring m in here, right? We know we need, since m divides x minus x, that means x minus x equals m times some integer. Well, m times 0, 0 is an integer, that equals 0, because m is a positive fixed integer, so that equals 0. And that also equals x minus x, because that's an integer. Okay, so thus m divides x minus x. So we can say that congruency mod is reflexive on Z. Okay, so you might want to again think about that, and hopefully you understand how we could say that and why we shown that we've proven reflexive. Okay, now let's look at symmetric. So you have to prove it's symmetric. So here we need to involve two variables. So let x and y belong to the integers, and suppose, okay, remember here, symmetric, we have that conditional statement. So we need to suppose x relates y. Well, in this example, that means suppose x equals y mod m. We need to show that y equals x mod m. Okay. And again, I would advise you to stop the video because I'm going to pause this and write out the rest of the solution and see if you can follow along or see if you can prove symmetry on this. Okay, so hopefully again you've proven that and it looks similar to this or along the same concept. So we suppose x equals y mod m. We needed to show that y equals x mod m. So that means m divides x minus y. Well, by definition then, x minus y equals m times p for some integer p. And again, keeping in mind what we're trying to show m divides y minus x. So we can just multiply both sides of what we do have by -1. And so we'll have y minus x equals, and that'll give us y minus x equals m times negative p, or negative mp, and then I rewrote that as m times negative p. So first, multiply both sides by -1 there, and then once you reorganize and simplify, that becomes y minus x equals m times negative p. And of course, since p belongs to the integers, negative p also belongs to the integers. Thus, m divides y minus x, hence the congruent mod is symmetric on Z. Okay. Now, transitive, so I'm actually going to advise you to pause here. I'm just going to write transitive, and I want to see if you can actually set up this last proof, if you can set this up, this last part of the proof, I should say, and then see if you can solve it and then play the video. Okay, so hopefully you tried the transitive property, and first we let x, y, and z belong to the integers. Suppose Remember again, transitive is a conditional statement. So we're supposing x equals y mod m and y equals z mod m. That's what's given to us. And we need to show that x equals z mod m. Okay. So from what our supposition was, from x equals y mod m, we know that means m divides x minus y. And because y equals z mod m, m divides y minus z. And I'm using sort of more shorthand notation, so feel free to use this as well, because again, we're getting more sophisticated with our proofs now. So that means there exists R and S belonging to the integers such that, I don't know if I ever used that in class, but ST means such that x minus y equals m times R and y minus z equals m times S. Okay, so we're trying to show x equals z mod m, so we're trying to show that m divides x minus z. Well, we see if we add x minus y and y plus z together, we get x minus z. So x minus z, okay, so my video stopped, I'm not for sure where, but basically we have x minus z equals x minus y plus minus z, which equals mr plus ms, which equals m times r plus s. And since r and s are integers, r plus s is also an integer. Okay, so hence we just showed x equals z mod m. So our congruent m is transitive on z. Our congruency module is transitive on z. Therefore, since we proved it was reflexive, symmetric, and transitive, the congruence mod m is an equivalence relation on z. Okay, good. So again, you can stop the video, write this down, because I'm just going to go over this rather quickly. Now, we already know what equivalence classes are. Well, the equivalence class, so definition, the equivalence class for the relation that congruent modulo m, let me make sure I'm saying that right. Yes, congruent modulo m is denoted by z sub m. And so, for example, z sub 3 represents the set of all equivalence classes of mod 3. Thus, for an integer in z, the equivalence class of x in mod 3 equals the set y belonging to the integer such that x is congruent to y mod 3. Okay, that's how that's read. Okay, so for instance, the equivalence classes, and I believe we talked about in class in terms of equivalence classes, either they are equal or disjoint, so keep that in mind. So for the equivalence class of 0, it's the elements, it's a set of starting from negative, negative 3, 0, 3, 6, The equivalence class of 1, again, we're in mod 3. Again, it's an infinite sort of set, but it has a pattern. So it's negative 2, 1, 4, And then the equivalence class of 2 equals negative 4, negative 1, 2, Okay, so therefore that means that the equivalence class of Z3 is equal to the equivalence class of 0, 1, and 2. Okay, it's a set of the sets of equivalence classes. And notice here, and so I have it on the next slide that you're going to write it down, but what you notice is that for, say, 0, and we talked about that 0 is actually congruent to every multiple of 3 in mod 3. And in order to get this set, it's either repeated addition or subtraction on your mod m, whatever m is. And so since m is 3 in this case, we just did repeated either addition or subtraction from 0. So from 0, you see, if we subtracted 3, we get negative 3. We subtracted 3 more, it would be negative 6, and so on. And if we added 3, we get the positive 3, and so on. And so the same rule applies with the equivalence class of 1. Okay, we subtract 3, we get negative 2, and so on. And then we add 3, we get 4. Okay, and so that's how we get z sub 3 is equal to the equivalence class, or the set containing 0, the equivalence class of 0, the equivalence class of 1, and the equivalence class of 2. So I'm actually going to stop this video here. So this will be 2 videos, but the second video is going to be really short because, again, I don't want to go over 20 minutes. I just want to stop this video here, and then we'll pick up on the next video.